So, welcome to this lecture number 20 in our discussion of fluid mechanics, low Reynolds number flows. If you recall, in the last class we had a little bit to complete on the torque exerted on a particle which is rotating in Stokes flow. So, going back to our discussion, then we had a spherical particle with center at the origin, which was rotating with an angular velocity omega. Now, the velocity field at the surface of the sphere is equal to omega cross r vector. Okay. So, this was our spherical particle which was rotating with angular velocity omega. Omega cross x is the linear velocity at points on the surface of the particle. Okay. So, we are supposed to solve the Stokes equations with this boundary condition. As you recall, the way that we solved it was that since these equations, the velocity solution for the velocity field satisfies Stokes flow equations, the solution has to be linear in this velocity omega as well as linear in one of the spherical harmonics. It cannot be just a linear function of omega, because omega is a pseudo vector, whereas the velocity itself is a real vector. Therefore, it can only be a linear function of epsilon dot omega. Epsilon antisymmetric tensor, epsilon dot omega gives you a second order tensor, because epsilon is third order and omega is a first order vector. So, therefore, we had taken a general solution that had three components. Okay, one is due to the dotting of dot product of epsilon dot omega, which is second order, with a first order vector, and then dot product of that with the second order with a third order tensor. So, third order tensor double dot product with a second order tensor, that is epsilon dot omega, will give you a vector. Similarly, pressure is a scalar, epsilon dot omega second order tensor. So, you have to take two dot products of that with the second order tensor to get the pressure. However, both of these turn out to be 0. Okay. Both of these terms here turn out to be 0, because as I just showed you, these are products of an antisymmetric and a symmetric tensor. Okay. Both of these are products of symmetric and antisymmetric tensor. So, for the velocity field, you are left with just one solution, which is the dot product of epsilon dot omega, okay, with the first order vector solution of the Stokes of the Laplace equation. And it is quite easy to get a solution that satisfies the boundary condition. Okay. So, that was our solution, it was simple. However, in order to find out the torque that is exerted on the sphere, we have to find out the stress tensor. Okay. The torque can be written as integral over the surface of x cross f. F itself is written in terms of the stress tensor at the surface. The stress tensor is related to the velocity gradients, okay, as you recall in the last lecture. We do not have a pressure here, because the pressure is equal to 0, but still we have a velocity field and we need to take its gradient, and the stress tensor is related to the gradients of the velocity field. So, we had calculated the two gradients of the velocity field. Okay. We had taken the gradients of the velocity field here, multiplied that by the viscosity, and then dotted it with the unit normal. Okay. Unit normal NL is equal to XL by R, where XL is the position vector and R is the distance from the origin. Okay. And I showed you that when you take this dot product, there is one term which vanishes, because it contains a symmetric times an antisymmetric tensor. If you recall here, epsilon LMN is antisymmetric in N and L. Okay. In other words, if you interchange N and L, you get the negative result, whereas this one xn, xk, xl is symmetric. So, when you multiply those two, you get 0. And then when we looked at the other two terms here, okay, these first two terms here, okay, this one and this one, I had showed you that they are opposite of each other, because I have epsilon kml and I have epsilon lmk. Okay. Epsilon lmk is equal to epsilon klm. Okay. That is when you do the permutation of the indices, which is minus epsilon kml. Okay. And because of that, these two cancel out and you get 0, and I get just one expression which survives, okay, for the force acting at a given location on the surface, that is of this form. that is the force exerted per unit area on the surface. If I just take this force and I integrate it over the entire surface, I will get 0. The reason is simple. This force is an odd function of the position vector. It is an odd function of the position vector. So, it is proportional to x1, x2, x3 components of that position vector. When you take an odd function of the position vector integrated over a closed surface, you will end up getting 0, because for each value of plus x1 on that surface, there is a value of minus x1 as well. Okay. It is an odd function. When you integrate an odd function over the entire surface, you will get 0. This is true for all odd functions. A function that is linear in x vector will be 0, one that is cubic will also be 0, fifth power will be 0, and so on. Okay. So, if I take this expression for the force and just integrate it simplistically over the entire surface, I will get 0. That is because a rotating sphere should not experience a force in any particular direction at Stokes flow, okay, because it is a linear function. It is different at higher Reynolds numbers, because at higher Reynolds numbers these are not linear functions. So, rotating sphere at higher Reynolds numbers can experience a force. However, at low Reynolds numbers, because the force and the angular velocity have to be related in a linear fashion, angular velocity is a pseudo vector. Okay. So, therefore, the force has to be related to epsilon I j k times omega k. Epsilon I j k times omega k is a second order tensor. There is no way to get a real vector out of that, and therefore, the net force has to be equal to 0. However, the torque is also a pseudo vector. The direction of the torque also changes sign when you go from right to left handed coordinate system. Therefore, you can get a net torque due to a rotating sphere, and that net torque is obtained by taking the cross product of the position vector on the surface, the cross product of the position vector on the surface and the force on the surface. When you take the cross product, force has epsilon k m n times omega m x n, then the cross product of that with x has another epsilon. I told and I gave you a formula in the previous class which will simplify this calculation. Product of two epsilons, two antisymmetric tensors has to be, the product of two pseudo tensors has to be a real tensor, because each one reverses sign when you go from right handed to left handed coordinate system. Therefore, the product of these two has to be something that does not change sign. Fourth order tensor, which is real, and it is also independent of coordinate systems. Epsilons are independent of coordinate systems, they are always equal to plus 1, minus 1 or 0. Therefore, the product of 2 also has to be independent of coordinate systems. And as I said, you can construct a fourth order tensor by taking the tensor product of two second order tensors, that is the identity tensors, and there is an exact expression which relates the product of two antisymmetric tensors with two identity tensors. And so, we had used this in order to find out what is the expression for the torque. Okay. So, when I expressed it in terms of delta I m, delta j n and delta I n, delta j m, okay, I get one that is equal to omega I times x j square minus x I x j omega j. Okay. So, let us just write this expression once again for clarity, minus 3 mu r cubed by r power 4. Okay. I should have a surface integral here, okay, into omega I integral ds. X j square is just r square, okay, just equal to r square itself, minus omega j integral ds x I x j. Integral ds of x j of r square is just equal to the surface area times r square, okay, because r is just the distance from the origin to the surface of the sphere. Okay. So, on the surface of the sphere, okay, the torque at r is equal to capital R minus 3 mu r cubed by r power 4, r is equal to capital R on the surface of the sphere. I will get omega I times r is equal to capital R on the surface of the sphere times the surface integral. So, this is just equal to r square times 4 pi r square. Okay. And I have the second term here, okay, integral ds of xi xj. This is an integral over the entire surface of the sphere xi xj. Okay. Now, there is no direction in this field because the sphere surface itself is isotropic. Once I integrate over the entire surface of the sphere, I cannot get a result which is which depends upon any particular direction because this integral itself is isotropic. Second order tensor isotropic. Therefore, it has to be some constant times the identity tensor, okay, because it cannot depend upon any particular direction. Okay. If for example, I were integrating something over an object like this, okay, that object has a net direction p, okay, the orientation of the axis of this object. If I integrate xi xj over this object, I could get something that depends upon this vector p. Okay. So, for example, I would get something that could be written as plus pi pj. Okay. But a sphere itself is an isotropic object. A sphere itself is an isotropic object. There is no net direction here. Okay. Since there is no vector direction, the result that I should get will depend only upon the identity tensor, which is an isotropic tensor in 3 dimensions. Okay. So, how do I find out what is the value of A? Okay. The answer is quite simple. I can multiply both sides by delta ij. Okay. I multiply both sides by delta ij. Okay. Integral ds xi xj times delta ij is just xi square is equal to A times delta ij times delta ij. In one of those I replace j by I and I just get delta ii. Okay. What is the value of delta ii? Is equal to delta 1 1 plus delta 2 2 plus delta 3 3. One repeated index, that means there is summation, no unit vectors. So, delta 1 1 plus delta 2 2 plus delta 3 3 in 3 dimensions is just equal to 3. Okay. And on the left hand side, I have integral ds of xi square. Xi square is capital R square on the surface. Okay. So, therefore, integral ds of xi square is just equal to the surface area 4 pi r square times r square. So, this becomes 4 pi r power 4. Okay. So, that is equal to 3a, which means that a is equal to 4 by 3 pi r power 4, okay. A times delta ij. Okay. So, this is equal to 4 by 3 pi r power 4 delta ij. Okay. So, use that in this expression minus omega j 4 by 3 pi r cubed delta ij. Omega j times delta ij is just omega I. Okay. Omega j times delta ij is just omega I. Okay. So, this 4 pi r power 4 times this should be r power 4. Okay. So, 4 pi r power 4 times delta ij minus 4 by 3 pi r power 4 delta ij, this gives me 8 by 3 pi. Okay. This becomes minus 8 pi mu r cubed. Omega I. Okay. So, this is the expression for the torque acting on a spherical particle. So, torque acting on the sphere due to the fluid is in the direction opposite to the direction of rotation of the sphere. whereas the torque that the sphere exerts on the fluid will be in the same direction as the rotation of the sphere. Okay. So, recall the velocity field that I had. Okay. When I solved for this expression, the velocity field that I had was u I is equal to epsilon I j k omega k r cubed, let me see, omega j x k r cubed by r cubed. That was my expression for the velocity field. And instead of expressing this in terms of the angular velocity, I could also express it in terms of the torque. Okay. So, I just use this relation to rewrite the angular velocity in terms of the torque. So, the angular velocity becomes 1 by 8 pi mu r cubed. Okay. So, this if I write it in terms of the torque, I will get epsilon I j k omega j L k, okay, by 8 pi, I am sorry, epsilon I j k L j x k by 8 pi mu r cubed. Okay. Once again, an important point to note, when the velocity field is expressed in terms of the torque rather than the angular velocity of the sphere, the final result is independent of the radius of the sphere. It depends only upon the torque exerted by the sphere. So, this is like the solution that we had, the Oseen tensor for the fluid due to a linear velocity. In that case, the velocity when expressed in terms of the force, the slowest decaying component, the component proportional to 1 over r, was independent of the radius of the sphere. So, it depended only upon the force and the distance from that force for that velocity disturbance. That velocity disturbance decreased as 1 over r and is proportional to the force. For a rotating sphere, the velocity disturbance decays as 1 over r square. So, this is a dipole, okay, a dipole disturbance. As we will see, it is an antisymmetric part of the dipole moment. Okay. It is proportional to the torque, okay, and it does not depend upon the radius of the sphere. So, in a sense, this is a solution that is a solution for a point particle that is rotating in the limit as r going to 0, provided the torque remains a constant, the velocity disturbance will depend only upon the torque. Okay. So, this is for a rotating sphere. Okay. Let us go on to our next fundamental problem. Okay. So, we looked at a sphere that was translating in a fluid, a sphere that was rotating. Okay. So, there are 3 different kinds of deformations that we had seen earlier at a point. Okay. One is radial expansion or compression, antisymmetric part of the deformation tensor which related to the local rotation. Third was the symmetric part, which was due to pure extensional shear. Okay. So, firstly we discussed the net force exerted due to a sphere on the particle. Then for a rotating particle, the rotation, the disturbance to the velocity field due to the rotation of the sphere. The next example relates to a sphere placed in an extensional field. So, what is the disturbance due to a particle which is placed in a velocity field which undergoes extensional flow far away from the particle. Okay. So, this example relates to having a particle in a velocity field, okay, where far away from the particle you have an extensional flow. Okay. So, if the particle were not present, the streamlines would all go like this. You would have the pure extensional flow in which the velocity streamlines are u I is equal to this tensor times the vector x j. Okay. So, this was what we had analyzed for extensional flow, and I told you that this is the only part of the rate of deformation tensor that results in stresses. The question we are going to ask here is, if I have a sphere, okay, we know that the net velocity past that sphere is going to cause a net force. Net rotation of that sphere or the net rotation of the fluid relative to that sphere at that location is going to cause a torque. Okay. What does this type of deformation, what is the velocity disturbance cause due to this type of deformation? What is the practical application that it can be used for? Okay. So, let us just discuss that in a little. This is for the effective viscosity of a suspension. Is the effective viscosity of a suspension. Let us say I had a suspension of solid particles. And I imposed a velocity field, and I calculated the stress as a function of the strain rate. Okay. So, the stress will be equal to, or in this case, since it is 2 dimensional, let me just take an x y coordinate system. Tau x y is equal to some viscosity, I will call it as an effective viscosity, partial u x by partial y. If I had a, this distance was L into the macroscopic strain rate 2 v by L. So, since I have plates moving with plus and minus v, the net relative velocity is 2 v separated by distance L. Therefore, the macroscopic strain rate is 2 v by L. Okay. Of course, if I had no particles, then the viscosity would be just the fluid viscosity mu. Okay. If there are no particles present, the viscosity would be just the fluid viscosity mu. However, I have these particles that are present in the fluid, therefore, the viscosity is going to be different from the fluid viscosity mu. How does the presence of the particles affect the viscosity of the fluid? Okay, so, that is the question. How is mu effective related to the number of particles, their mass density and so on? Okay, so, that is the question. We will consider this only in what is called the dilute limit. Only in the dilute limit. The assumption here is that the velocity field, okay, the velocity disturbance due to one particle. So, if I have one particle that is moving in some direction, that is causing a velocity disturbance in the fluid. Okay. There is a small velocity disturbance due to one particle in the fluid. In the dilute limit, the assumption is that this velocity disturbance does not affect another particle. So, the particles are sufficiently well separated that the velocity disturbance around one particle does not affect another particle. Okay. So, that is what I meant by dilute limit. It is like the ideal gas limit in the virial expansion for gases, for example. You assume that there is no interaction between molecules in that case. So, similarly, in this case you assume there is no interaction between particles, okay, in this dilute limit. So, it is in that limit that we are trying to analyze the problem. Okay. So, here we need to find out the ratio of the stress and the strain rate. Okay. Now, I will define the stress, okay, Tij, the average stress, okay, the total stress of this entire fluid plus particles, okay, the entire system which consists of both fluid and particles. There are different ways to define it. Okay, the most convenient way is to take that as a volume integral of the total stress. The most convenient way is to assume that this is the volume integral. The average stress is the volume integral over the entire domain of the local stress at each point, okay, within that domain. Okay, so, that is the total stress. Now, the simplistic way to separate out this stress is to write this as 1 over V integral separated into two parts. One is over the fluid Tij plus the integral of the particles. Okay. One is to separate out into one part over the fluid, the other part over the particles. Okay. However, we will use a different method to do this, a method that makes the particle contribution clear, okay, in this entire thing. Okay. So, what I will do is that I will write down, okay, in this expression for T I j. Okay. I will write down as T I j plus P delta I j minus 2 mu E I j. Okay. Okay. Where E I j is the rate of deformation tensor locally. Okay. E I j is the local rate of deformation tensor. I have made a simplification here. Okay. The simplification is that the rate of deformation tensor consists of two parts. One is the rotational part, the antisymmetric, and the other is the symmetric traceless. There is no isotropic part because the flow is incompressible. Okay. The density is a constant, so there is no radial component. There is an antisymmetric and a symmetric traceless part. Here my assumption is that the stress is not affected by the antisymmetric part. Okay. As I said, antisymmetric part causes only a rotation locally. It does not change the distance between nearby points in the fluid. Okay. So, I will write down the stress tensor in this manner, okay, and we will see how it works out. Integral over the entire volume plus integral over the entire volume of dV okay. So, that is the final, that is the expression for the stress tensor. Okay. Note that here I have taken mu as the fluid viscosity. Okay. So, I am adding and subtracting out the fluid viscosity times the symmetric traceless part of the rate of deformation tensor as also the pressure. Now, we know that the equation, the constitutive relation for the fluid stress tensor is T I j is equal to minus P delta I j plus 2 mu E I j. Okay. Therefore, what has happened is that in this expression, the integrand is 0 in the fluid. The integrand is 0 in the fluid, because in the fluid we know that T I j is minus P delta I j plus 2 mu times E I j. So, the integrand is 0 in the fluid. That means that this integral contains only the integral over the particles. Okay. Even though originally I had posted as an integral over the entire system, the integrand is 0 everywhere in the fluid, and therefore, the integral is only over the particles. Okay. Therefore, the average T I j is equal to 1 over V integral over the particles. Okay. And the second term here is a volume integral of the pressure and the symmetric part of the rate of deformation tensor averaged over the entire fluid. So, this is just the volume averaged, okay, pressure and the rate of deformation tensor in the fluid. Okay. So, this is just equal to minus average P delta I j plus 2 mu times E I j. Of course, this average symmetric part of the rate of deformation, symmetric traceless part of the rate of deformation tensor, the average value, that has to be equal to the macroscopic applied rate of deformation tensor. Okay. So, this average value is equal to what is the symmetric traceless part of the rate of deformation tensor, which is applied by the shearing of the two plates, okay, because what is averaged over the entire system has to be what is obtained by the macroscopic shear. Okay. So, there is the so now we have to so this is So, this is the viscosity that I would have got if there were no particles, because the integral over the particles would have been identically equal to 0. But since I have particles, these are causing a disturbance in the flow. Therefore, I get an integral which is in general non-zero, okay. And the task is to evaluate what this integral is. Okay. Now, first things first, this is the rate of deformation tensor within the particles. Okay, this is the rate of deformation tensor within the particles. Particles are rigid. Therefore, when you apply a stress on them, they deform and then stop. Okay. There is no continuous deformation upon application of stress. Therefore, this deformation tensor, rate of deformation tensor within the particles has to be identically equal to 0, okay, because particles do not deform continuously upon application of shear. Okay. Of course, there could be a compression of the particles, okay, but that will not result in a the symmetric traceless part of this volume average stress tensor. Okay. So, therefore, there could be some compression or expansion, but on average that will not result in a contribution to the symmetric traceless part of the rate of deformation tensor. Okay. Plus, okay, there could be some compression or expansion due to the particles. Okay. So, I will just leave that as a particle pressure delta I j minus the fluid pressure delta I j plus 2 mu times E I j. So, in order to calculate the effective viscosity, I have to find out what is the contribution of the particle stress. Okay. I have to find out what is the contribution due to the particle stress, okay, to the total stress, which is proportional to the average rate of deformation tensor. Okay. Total stress contribution proportional to the average rate of deformation tensor. These two parts are the isotropic parts, okay, which will not contribute to the viscosity of the system. Okay. So, I have to calculate what is integral over the particles integral dV of T I j. So, first things first, I have to calculate 1 over V integral over all the particles dV of T I j. Okay. Assumed that the solution, that the suspension was dilute, the particles do not interact with each other. Okay. That means, the integral over all n particles of dV times T I j is going to be equal to the number of particles divided by the volume integral over one particle, integral over the one particle dV T I j of, okay, times the number of particles per unit volume, because all of these particles are in a macroscopic flow field in which there is some deformation that is taking place. There is symmetric traceless deformation that is taking place, because of which you are getting a net contribution to the stress, okay, within the particles. Okay. So, this one particle is now being placed in an extensional flow. As I said, the rotational part of the velocity field does not contribute to the stress, it is only the extensional part. So, this particle is being placed in an extensional flow, and you have to calculate this integral over the particle volume of dV times T I j. Now, we do not have the constitutive relation for the elastic deformation within the particle. Okay. So, we cannot just calculate this integral straight away, because we do not have a constitutive relation for the elastic deformation within the particle. Okay. Rather, what we can do is to rewrite this T I j. Okay. So, let me just rewrite it. Okay. Of T I, okay, if you take this derivative partial by partial x L of T I L x j. Okay, if you take this derivative partial by partial x L of T I L x j, okay, this will be equal to partial by partial x L of T I L times x j plus T I L partial x j by partial x L. Okay. The second part is just delta J L, okay, T I L delta J L. The first part is x j times the divergence. Okay. Now, for the solid, if you assume that the inertial effects in the solid are negligible, then the divergence of the stress within the solid has to be equal to 0, okay, because the divergence of the stress within the solid is also balanced by inertia and by body forces. Okay. The viscous forces in the fluid are comparable to the viscous forces in the solid, because you have to have continuity of stress boundary conditions at the surface. If the solid inertia is small, then the elastic forces in the solid, okay, are large compared to inertial forces in the solid, which means that the divergence of the stress within the solid has to be equal to 0. Okay. So, this is an additional piece of information that I will use, that because inertia is neglected in the fluid, if the density of fluid and solid are comparable, then inertia can be neglected in the solid as well. And even though the constitutive relations are very different, okay, for a solid elasticity and fluid viscosity, viscous flow of a fluid and the elastic deformation of a solid, the constitutive relations are very different, but the momentum conservation equation will still tell you that the divergence of the stress is balanced by the body forces and inertial forces. And if those are negligible, the divergence of the stress in the solid also has to be equal to 0. Okay. So, if this is equal to 0, okay, I just get that partial by partial x L of T I L x j is equal to T I j, that is the stress tensor itself. So, this is a little bit of additional information that I have used about the solid itself, okay, which is not clear a priori, but provided I can neglect inertia in the solid, the mass is not too high, I can always neglect the divergence of the stress tensor within the solid. So, now for this T I j, I can substitute this divergence. Okay. So, therefore, 1 by V integral dV of T I j over 1 particle is equal to 1 over V integral dV of partial by partial x L T I L x j over 1 particle. Okay. Now, this divergence of something integrated over a volume is equal to that dotted with the unit normal integrated over the surface, divergence theorem. Okay. So, this is equal to 1 over V integral over 1 particle dV T I L N L times x j, okay, the unit normal, because I had a divergence with respect to the index L, therefore, I have to substitute the unit normal also with index L. Okay. So, this is an integral over 1 particle of the stress unit normal times the position vector integrated over that particle. Of course, I still do not have the constitutive relation for the stress for the particle. However, I know that the particle stress on the surface has to be equal to the fluid stress on the surface. Therefore, in this expression for the stress, rather than using the fluid stress, I can use the particle, rather than using the particle stress, I can use the fluid stress here, and that is the advantage of this. I have reduced it to a surface integral, where I have managed to get the fluid stress on the surface in the integral, and once I have that, I can actually solve it. How do you solve this? Okay. So, this is solution for in extensional flow. Okay. So, I have a particle which is in an extensional flow field, far away. I have a particle in an extensional flow field far away, and the velocity u I is equal to Eij times xj. That is the extensional flow field in the limit as you go far away from the sphere as r goes to infinity. And at the surface itself, because it is rigid, okay, there is no rotational part, so it is not rotating. Therefore, the velocity field itself has to be equal to 0 at the surface at r is equal to capital R. So, now we have to solve for the velocity profile for an extensional flow far away from the sphere and velocity equal to 0 on the surface in order to find out what is the velocity disturbance, okay, due to the sphere. Okay. So, the velocity, the fluid velocity field of course will contain one component, okay, will contain one component which is just the extensional flow very far away, okay, plus a disturbance due to the sphere, okay, because the sphere is imposing 0 velocity boundary conditions on its surface. There is going to be a disturbance to the velocity field due to the sphere. How do you get that disturbance? Both the pressure and the velocity field, okay, the general part of the general solution for the velocity field and the pressure have to satisfy Laplace equations. They have to be linear in one of the harmonics. We have to take only the decaying harmonics because the velocity field disturbance has to decrease as we go far away from the sphere. Okay. This imposed velocity is already here. So, the other part which is the disturbance has to decrease as you go far away. It has to be linear in one of the decaying harmonics and it has to be linear in this tensor Eij, okay, not in Eij xj. Xj is a field dependent quantity, it depends upon position. Okay. What is forcing this flow is the symmetric traceless part of the deformation tensor Eij itself. That is a constant here, okay. Just as the velocity of the sphere for the translating sphere was a constant, angular velocity of the rotating sphere was a constant. So, we required that the velocity should be linear in that. Similarly, in this case Eij is the constant, Eij xj depends upon position. Okay. So, the forcing function here is the symmetric traceless second order tensor Eij. So, using these I have now got to construct solutions. Okay. So, from the second order tensor I can have a velocity vector created in two ways, Eij dotted with a vector okay, that is the decaying vector decaying spherical harmonic plus A2 Ejk phi 3 Ijk. Okay. So, that is the general part of the velocity field. The pressure is equal to A3, it has to be linear in E. Okay. The only way you will get a scalar is to double dot it with the second order tensor decaying spherical harmonic. Okay. And then you have to determine constants A1, A2 and A3 from the incompressibility condition, divergence of velocity is equal to 0, as well as these boundary conditions here. Okay. I will not go into the details of how that calculation is done. Okay. The only thing that I would note is that since this is a symmetric traceless rate of deformation tensor, I can use the fact that Eii, okay, that is E11 plus E22 E33, which is equal to Eij times delta ij, that has to be equal to 0. Okay. So, that is a simplification that can be used, and once you use that simplification you will get a solution for the velocity field. Okay. So, I will just give you the final solution for the velocity field. Okay. The final velocity field is Ui is equal to Eij xj into 1 minus r power 5 by r power 5 plus Ejk, there should be 5 by 2 there. Xi, xj, xk into r power 5 by r power 7 minus r cube by r power 5. Okay, so, that is the final solution for the velocity field after using the simplification that the trace of E has to be equal to 0. Okay. The final expression for the pressure is equal to minus 5 mu r cubed x j x k e j k by r power 5. Okay. So, these are the two, velocity and the pressure fields. Okay. Note that the disturbance to the velocity field, the slowest decaying part of the disturbance to the velocity field actually is this one. Okay. That is because that disturbance, okay, this part of the disturbance goes as r cubed by r power 5 times x I x j x k. Okay. X I x j x k goes as r cubed. Okay. X 1 is r sin theta cos phi, x 2 is r sin theta sin phi, and x 3 is r cos theta. Okay. If I have r cubed on top, r power 5 at the bottom, therefore, the slowest decaying term goes as 1 over r square. Okay. These other terms here go as 1 over r to the 4th, that is these two terms actually decay as 1 over r to the 4th. Okay. You can easily verify that. Okay. So, this is a dipole contribution. The source due to a net force was 1 over r. This is a dipole contribution. So, using these expressions, I can now go ahead and calculate the stress tensor minus p delta I j plus mu into partial u I by partial x j plus partial u j by partial x I. Involves a little bit of algebra. Okay. It might be worth your while to try and go through it. I will just give you the final result here. Okay. If you actually go ahead and calculate the final result, integral over the surface of ds of tau of T I L and L x j turns out to be equal to 20 pi r cubed mu E I j by 3. Okay, so, that is the final expression for the integral of the stress dotted with the unit normal. So, this is the force times the position vector Okay. If you recall the expression for the average stress, okay, the expression for the average stress that we had was n by v times integral over one particle of dv times t I j. Okay. So, therefore, this dv times t I j I substitute as 1 over 1 particle of t I L n L x j. So, put all of these together. Is equal to n by v integral over one particle ds t I L n L x j. Okay. Then I had this minus the particle pressure delta I j plus the fluid contribution delta I j plus 2 mu times E I j. Okay. Where E I j is the average stress that is applied on the entire system. Okay. That is also the the average rate of deformation applied on the entire system. That is also what is driving the particle stress here. Okay. So, this is equal to n by v into 20 pi r cubed mu E I j by 3. Okay. That is the integral over one particle. Okay. Okay. So, that is the integral over one particle. N by v, number per unit volume, okay, it will be equal to the volume of the total, okay, the number of particles per unit volume, okay, is going to be equal to the volume fraction divided by the volume of one particle. Okay. Because the total volume of all the particles, is equal to number of particles times the volume of one particle. Okay. So, V particle is equal to number of particles into the volume of one particle, 4 by 3 pi r cubed. Okay. Therefore, the volume fraction, which I will call here as phi, is equal to the volume of all the particles, okay, the volume of all the particles divided by the total volume is equal to n into 4 by 3 pi r cube, divided by, which means that n by v is equal to the volume fraction by 4 by 3 pi r cube. Let me just write that more clearly for you. N by v is equal to 5 by 4 by 3 pi r cube, where phi is the volume fraction. Okay. So, I can substitute for n by v in this expression, okay, 5 by 4 by 3 pi r cubed. Okay. If I substitute n by v is 5 by 4 by 3 pi r cubed, okay, what you get is 5 phi mu e I j, okay, because 20 by 3 divided by 4 by 3 just gives me a factor of 5, okay, plus 2 mu e I j plus the isotropic part. Okay. Okay. And I can add these two to give 2 mu into 1 plus 5 phi by 2, okay, e I j. Okay, so, this can be written as 2 mu effective e I j. Okay. So, therefore, we have got the contribution to the viscosity due to the presence of all of these particles. It does not depend upon the particle radius, it does not depend upon the number of particles, it depends only upon the particle volume fraction. Okay. So, the effective viscosity of a suspension of particles, okay, mu effective is equal to mu, the viscosity of the fluid, times 1 plus 5 phi by 2. Okay. This is called the Einstein viscosity. To reiterate, this effective viscosity of a suspension is only in the limit of dilute small volume fraction, so that the particles are non-interacting, that is, the velocity field around one particle is not disturbed by the presence of the motion of the other particle. In that case, the effective viscosity of a suspension of particles in the limit of low Reynolds number is equal to the fluid viscosity times 1 plus 5 phi by 2. Okay. So, this is a significant result. This tells you how the effective viscosity of a suspension is related to the volume fraction of particles in that suspension. If you recall, in Fundamentals of Transport Processes 1, we had derived a similar result for the effective thermal conductivity of a suspension. It followed a similar procedure, except that in that case we had done the calculations in terms of the Legendre polynomial expansion for the temperature field. In this case, we had solutions for the velocity and the pressure field, and from the moment, okay, the force moment, okay, interpretation of this term, it is TIL times NL is the force acting on the surface, times xj. TIL NL is just the Fi, the force acting on the surface, times xj. So, it is a force moment. It is a second order tensor, it is not the cross product as in the case of the torque. So, based upon this force moment on the surface, we have calculated the correction to the viscosity. So, this result is equal to the fluid viscosity times 1 plus phi by 2 phi, predicts that the viscosity of the suspension increases linearly with the volume fraction of particles in the dilute limit, in the limit where there is no interaction between pairs of particles. Okay. So, if I plot the volume fraction versus the viscosity effective I can just plot it as a ratio of effective viscosity by the fluid viscosity itself. Okay. There are no particles, volume fraction is 0, the fluid viscosity is equal to the effective viscosity and the ratio just becomes 1. As I add a small number of particles, I get this linear relationship, okay, with a slope that is given by phi by 2, okay, 1 plus phi by 2 phi, that is a slope very close to the origin. Of course, as the volume fraction increases, there is going to start to be interactions between particles, okay, and the calculation of the viscosity due to interaction between particles is a complicated one. Okay. It turns out that the next correction turns out to be, let me just 6.5 phi square. Okay. So, the correction of the quadratic, the viscosity due to the quadratic term turns out to be 6.5 phi square. This calculation of the next term takes into account the interaction between pairs of particles. If you have a particle at one location, you find out what is the contribution due to all other particles, the disturbance caused due to those, okay, on this particle that is located at one particular location, average that out to find out what is the effective viscosity. Turns out it is not as simple as imagined, okay, and the reason is because of the decay of this of the disturbance that I talked to you briefly about. Okay. The slowest decaying contribution to the velocity here goes as 1 over r square. Okay. As I said, it is a dipole term. If I try to integrate over the entire volume, that is at a given location x, the decay due to the velocity disturbance due to another particle located at distance r decreases as 1 over r square. If I try to integrate over all space, the volume in space increases proportional to r cubed, and therefore, I will get something that increases, that diverges as r goes to infinity. Okay. Turns out that you have to do the calculation carefully, take into account the renormalization of the forces. Effectively, you have to take into account the force exerted on a single particle due to all other particles, but also take into account the fact that because of this interaction, there is going to be a screening of the force. Okay. A particle near the test particle is going to screen the effect of particles that are far away. And once you do that, you get a coefficient of 6.5 phi square. Okay. This was first calculated by Batchelor in the context of viscous flows. Of course, as you start putting in more and more particles, the viscosity is going to keep increasing, and there is a limit. Okay. You cannot, if the volume fraction goes beyond about 64 or 65%, okay, at this limit the entire suspension is full of particles, and because the particles are rigid, okay, if you just have large numbers of particles in between, okay, okay, and if these are rigid particles, you will find that you will not be able to deform at all. That means that the viscosity has to go to infinity, okay, at this point. Okay. It has to go to infinity at a volume fraction of about 64 or 65%, because you cannot deform a fluid which is filled with so many particles, the particles cannot go past each other. Okay. So, that is how the viscosity of a suspension varies as a function of volume fraction. In this lecture, we have calculated only this one term, okay, for a dilute limit, but you can experimentally determine the viscosity even if very dense limit, and it will diverge at 64%. So, hope you found this interesting. This Einstein viscosity is actually quite a significant result, which was evaluated even without using many of the techniques we used here. So, it was a pretty formidable calculation. We have done the disturbance due to an extensional flow, a rotational flow, as well as a translating sphere. These three can now be put together. We will look at that in a little detail in the next lecture. We will see you then.